Hello friends, in this lecture I am going to discuss the optical waveguide and guided modes and we'll understand why phase changes at total internal reflection. In previous video I have discussed the concept of phase, concept of polarization, the concept of interference and guided modes. Now let me discuss why the phase changes upon total internal reflection. I have discussed this also. Reflection coefficient is nothing but E reflected by E transmitted. When this is the waveguide with refractive index N1 and outside there is N2, and this is the incident wave with angle theta 1. This is the transmitted wave, this is the reflected wave. So suppose here this is the general condition where total internal reflection has not happened. In general, this reflection coefficient is given by this equation: R is equal to n1 cos theta 1 minus n2 cos theta 2 divided by n1 cos theta 1 plus n2 cos theta 2, where theta 1 is this incident angle and theta 2 is nothing but this angle theta 2. When it transmits, it makes angle theta 2. So this equation, reflection coefficient, is called the Fresnel equation. So this is in general equation. There is no condition of the total internal reflection applied here. Now if we'll apply the condition of total internal reflection here, what will happen? So convert this equation in the form of theta 1. So how to convert? All these functions are at the form of theta 1. So we first convert this cos theta. Cos theta is equal to square root 1 minus sin square theta, and then sin theta, if it is theta 2, what will happen? Then this sin theta 2 can be converted using the Snell's law into sin theta 1. So next is n1 sin theta 1 is equal to n2 sin theta 2, Snell's law. So what will be sin theta 2 then? Sin theta 2 is equal to n1 by n2 sin theta 1. So we can convert cos theta 2 into sin theta 2 and sin theta 2 to in the form of sin theta 1. So after doing this conversion, what we will get, I am going to write that final equation. Now understand this. Critical angle sin theta c is equal to n2 by n1, we have written earlier. Now for this total internal reflection to occur, condition is theta 1 must be greater than theta c. So this equation was written for general condition. Theta can take any value. Now we are putting the condition for guided wave. We must have theta incident angle greater than critical angle. Then if we will take sine of both sides, sine of theta 1 must be greater than sine of theta c, because sine is the increasing function of theta. Now sine of theta 1 must be greater than, I am putting the value of sine theta c here. So sine theta c is equal to n2 by n1. So sine of theta 1 must be greater than n2 by n1 for which condition? Guided wave condition. Theta 1 is greater than critical angle. For that condition, what we are getting? Sin theta 1 must be greater than n2 by n1. So if you square both sides, sin square theta 1 must be greater than n2 square by n1 square. If you write this another way, if you multiply this right side, n1 this side, what will happen? n2 square must be greater than n1 square sin square theta 1. So just have to multiply this side. So if you subtract this thing this side, what is happening? Sorry, this is less than, this is going this side. So n2 square is less than n1 square sin square theta 1 from this equation. And now if I subtract this that side, so what we are getting, n2 square minus n1 square sin square theta 1 is less than 0. So this term within this square is becoming negative from this equation. N1 is n2 square minus n1 sin square theta 1 is nothing but negative, less than 0. So if something is negative in square root, it's complex number. So we can write this whole equation in this form. Now I am taking minus 1 outside, then it will become positive. So it's nothing but n1 cos theta 1 minus j times square root n1 sin square theta 1 minus n2 square and divided by same term n1 cos theta 1 plus square root plus j here also plus j square n1 square sin square theta 1 minus n2 square. So minus square root minus 1 I have taken out, which is nothing but the j imaginary number. So our reflection coefficient has become some a plus jb, a minus jb divided by a plus jb form. So this is the completely complex. Now if it is complex, we can write if r is equal to a plus a minus jb divided by a plus jb, so it's a mod of r into e power j theta. So this is the magnitude of the reflection coefficient, this is the phase of the reflection coefficient. So how to find mod r reflection coefficient? Here is nothing but square root a square plus b square divided by square root a square plus b square, so it is 1. So in reflection coefficient magnitude remains always 1. And what is the phase then? Phase is nothing but minus of tan inverse b by a for this, and this will be subtracted again, so minus of tan inverse b by a. So it is nothing but phase will be equal to phase of this r is nothing but equal to minus 2 times tan inverse b by a, and what is b and a, we can replace the value of b and a. So we have replaced B and A. So this much phase, negative of this much phase must change whenever it goes total internal reflection at the top or bottom surface. Why we are saying this top or bottom different? Suppose this is N1 refractive index, upper side is some medium N2 and bottom side is some another medium, say N3, then while reflecting here, there will be another phase change, says phi u, and when it reflects here, there will be phase change at the lower surface, that is phi l. Phi u and phi l will differ if n2 and n3 are different, because from this expression. So if it is the n2 and n3 are same, say air, it is called the symmetrical waveguide, and then this phi u and phi l remains same. But here is the proof of why there is the total internal reflection at some phase, and that phase must be written in the phasor equation while we solve the guided modes that I have discussed in the previous lecture. So after some simplification, we can find the phase change upon total internal reflection for TE mode is equal to minus 2 tan inverse sin square theta 1 minus n2 by n1 whole square divided by cos theta 1, and phase change for the TM mode upon the total internal reflection is equal to minus 2 tan inverse square root n1 by n2 whole square sin square theta 1 minus 1 whole divided by n2 by n1 cos theta 1. So this is in square root here also, square root. So these two things can be derived. I have derived this one. You can derive for TM also. So in previous lecture I have discussed if this is the planar waveguide with refractive index n1, and here is n2, here is also n2, same material both sides, but n1 should be greater than n2, and this is a light launched at angle theta 1. So this direction is k naught n1 is the propagation constant. In vertical direction this becomes k naught n1 into cos theta 1, and in one round trip total phase accumulated is nothing but the distance traveled is 2h into the propagation constant k naught n1 cos theta multiplied by this plus phase change here and here. So phase change at both will be same, so it is 2 pi must be equal to 2 pi m. So this is called the phasor equation, and when we put the value of phi, it becomes 4 tan inverse this. This must be equal to 2 pi m. So this phasor equation, you can see the transcendental equation. Here is theta 1, here is again theta 1. So you have to solve the theta 1 for different values of m. That gives the different modes of propagation. This expression can be rearranged. Here is the 2 minus 4, 2 can be cancelled out. Is the 10 inverse. You take all terms on one side and take this 10 of something is equal to this. So let me write that equation also. After rearranging, what you are getting. So after rearranging, we are getting this expression 10 of cannot n1 h cos theta 1 minus m pi divided by 2 is equal to square root sin square theta 1 minus n1 by n2 whole square divided by cos theta 1. So you can solve this expression in MATLAB. Take this y1 is equal to this expression and plot y1 as a function of theta 1, and you take this y2 and you plot y2 is equal to some function of g of theta 1. So if there is intersection point, that will be the solution. So those solutions are the angle of propagation and those are the modes of the propagation. After knowing this phasor equation, can you find what will be the maximum number of m? So m here is giving the number of modes. If for m is equal to 1, 2, 3, we are getting 3 values of theta, theta 1, theta 2, theta 3, and after that we are not getting any solution. So there are 3 modes. So the number of m, the value of m is the number of existing guided mode inside the waveguide. So how can we find this? So if we put this theta 1 exactly equal to critical angle theta c, so what will happen? The sin theta 1 will become sin theta 1 is nothing but then n2 by n1. So if we take square, what will be this? Sin theta 1 once again. Yeah, so here expression I have written wrong, is the n2 by n1. So in that case, theta 1 is critical angle, sin theta 1 becomes n2 by n1, and in square, this term will become 0. If this term is becoming 0, 10 of this is equal to 0. So what we will get? This is equal to 0. After solving, we will get then this time theta is equal to critical angle theta c, this term is becoming 0. So 10 of something is equal to 0 means this angle cannot, this will be equal to 0, and in that case we will be getting maximum value of m. So we can write m max here, m max into pi. So maximum number of existing mode can be given from this expression. So how will we get this? Is given 0 this. So m max is nothing but cannot n1 h cos theta 1 divided by 2 divided by pi. So this is the condition. But since we have put the condition theta is equal to theta 1 is equal to theta c, so we'll put here theta c. We can find this value also, cos theta c. Since sin theta c is equal to n2 by n1, so cos theta 2 theta c is equal to square root 1 minus n2 square by n1 square. So we can replace here this. So maximum value of m is becoming, maximum value of mode is nothing but k naught is 2 pi by lambda multiplied by n1 into h into cos theta is square root 1 minus n2 square by n1 square and whole divided by pi. So this pi cancels. We are getting 2 n1 h square root n1 square minus n2 square whole divided by lambda into n1. So this n1 cancels, so you can get this value 2h by lambda square root n1 square minus n2 square. So this is relative refractive index difference, you can say. So if you have relative refractive index difference, more number of guided mode will be there. If it is small, less number of guided mode will be there. If you have higher width, waveguide width very high, you will be getting more number of modes. If this width of the waveguide is small, less number of modes will be there. If lambda, if the longer wavelength is launched, fewer modes will be there. If shorter wavelength is launched, more modes will be there. So modes, no, number of modes m depends on which relative refractive index difference del, height h, and wavelength lambda. So this is very much important. You can solve some equation, some questions based on this equation. Thank you. Now we are in condition to solve the question we have asked earlier. Whenever light is launched at z equals 0 and travels some distance at z, at this point what will be the total phase accumulated within the waveguide? Now if it is in the free space, light is going straight line, we can multiply this z by k0. So k0 z will be the total phase in the free space if it is traveling in a straight line. But within the waveguide it is going in zigzag motion. So we need to find this total length, then multiplied by this k0 into n1, then we will get that phase. But here now we have broken this k0 and in two form, this direction and this direction. So in this direction it is kz, and kz is nothing but k0 n1 multiplied by the sine of theta 1. Since we have solved the phasor equation and we got the some solution of theta 1 using the some MATLAB program. So this theta 1, suppose we have different values for corresponding, suppose we have expression theta 1, theta 2, theta 3. These three solutions we got corresponding the mode m is equal to 1, 2, 3. So three modes are propagating. Suppose now corresponding to one angle theta 1, we have this value kz. Once we get this kz, we can find, so how much distance it's phase accumulated. So phase accumulated in z direction will be kz times z. Suppose this z is equal to z naught. So after traveling z distance, how much phase is accumulating now? K naught n1 sine theta 1 into z naught. So this is the solution we have reached. Now there is one concept of effective index. Let me write that also, effective index. Now the propagation constant in this direction along the waveguide is always known as beta. So kz is also written as the beta and phase is always written as beta z. So kz is nothing but the this z component of the k0. So k0 n1 sine theta 1. But generally beta is written in the form of k0 into n in the free space. Suppose it is free space, we write always beta, yeah, or some medium, there is no guided medium, there is no boundary, then we write beta propagation constant is equal to k0 n, and light propagates in that medium in straight line. Suppose this is some one medium and there is no boundary and light is propagating in straight line and its medium index is n, then what is beta? Beta is equal to k0 times n, where k0 is the free space propagation constant. K0 is given by 2 pi by lambda, and lambda is the wavelength of the light launched. So in one medium, if some medium is there with refractive index n, if there is no boundary in that medium, then propagation constant beta is equal to k0 n, and when medium comes, when boundary comes, it becomes guided wave, and there is some certain solutions of the theta. Corresponding to that theta, we have got this expression phi is equal to beta is equal to k0 n. But here beta is equal to k0 of this. What does it mean? Even though if there is zigzag motion, guided medium, we can model this guided medium as a free space medium, and not as a free space, as a medium with no boundary. If you want to model this bounded medium, which is guided medium, in the form of, if as if there is no boundary, we can write this, because this expression is nothing but the propagation constant without boundary, and this we came with boundary. So if you make some equivalence in these two, if you write this is equal to this cannot, and this n we are giving some name n effective. So n effective becomes n1 into sin theta 1. So if we n1 sin theta 1 we are keeping equal to n effective, then we can simply get beta is equal to k0 into n effective. This means when we multiply this n1 by sine of theta 1 is the solution of that phasor equation. This gives me the effective index by which light propagates within the medium and without any boundary. So if you take the boundary, you have to take this complete. If you want to remove the boundary and want to see so this wave is propagating in a straight line, then you have to put some another index. So if you put only n, you are not going to get this beta. So we need to keep some different value of n, and that is called the n effective index. So refractive index is nothing but n1 sine theta 1. With this refractive index, light within the waveguide propagates in the direction of propagation, that is the waveguide axis, with effective index given as n1 sine theta 1. Or effective index can be understood again like this. Suppose it's n1 is the medium and there is no boundary and light is propagating with beta is equal to k naught n1 in this medium. Now suppose I have put the boundary in that medium. This medium is there with refractive index n1. We have put boundary. Now this beta has become k naught times not n, some another value of n, and effective. With this boundary, beta propagates in the medium of refractive index n1, but it doesn't see the n1 here. It sees some another value of n when boundary comes, and then this n must be modified version of this n, and that modified version is nothing but n effective is n1 multiplied by the sine of theta 1, where theta 1 comes from the solution of that phasor equation. So here I stop this.